My name is Linda Lukas. I'm a children's book author, illustrator, and programmer. Welcome to my world. I'm from Helsinki, Finland, and my job is to write children's picture books about the wonderful world of technology. These books are called Hello Ruby, and they've been translated into over 30 different languages around the world. And they all tell a story about a little girl called Ruby and her wonderful adventures, and they also have unplugged activities. And the books have stories about the hardware of computers, coding, artificial intelligence, internet, and all kinds of fun and exciting things about the world of computer science. Because here is what I believe in. Stories are the fundamental way we learn about each other, we learn about ourselves, and we learn about the world that is surrounding us. And no one is really telling stories about the world of software. Somehow we have this idea that there is this world of machines and this world of humans, and I believe that we all belong together. This is what I believe in. If code is the next universal language, instead of grammar classes, we need more poetry lessons. And what I mean with that is the idea that if our children are going to be learning as their first foreign languages, Chinese and English and JavaScript, we need more pedagogical tools to help them understand the abstract notions of computer science and explore these topics on their hands and knees. And that might mean that we need to make more candies, algorithms out of candies. It might mean that we need to make gingerbread cookies and make them look like computer components. It might mean that we'll build a YouTube out of cardboard. But most of all, it means that we need to somehow meld together these two very distinct worlds. And many of the people you see here on the wall, you might already recognize. There's people like Loris Malaguzzi, Maria Montessori, Tove Jansson, these luminaries of childhood and education who had big ideas what it means to be a little person, what it means to grow up in a world, and so forth. But then there's this other suit of people, these computer scientists who equally had dreams about the world and what it should look like. People like Ada Lovelace, Charles Babbage, Grace Hopper, pictured over here. And I think it's by combining these two groups of people, the dreamers and the engineers, we get a computer pedagogy and a curriculum to suit the next generation of children. Already in the 1950s, it was Jean Piaget who said that we can't offer an entirely organized intellectual discipline by only giving kids these pre-organized vocabularies of content, that true learning is always grounded in action. And it is this grounding in action that we should be doing with computer science. It is not that we're teaching kids coding. It is not that we're teaching them ICT skills or social media skills. We are preparing the kids for a world where more and more problems around them are computer science problems. And we need a radically more diverse group of kids to get excited about computer science as a tool of self-expression and as a tool of problem solving. And that is where you, as a teacher, come in. There's this really famous quote that comes from Edgar Dijkstra, and it's often attributed to him, and he says that computer science is no more about computers than astronomy is about telescopes. And I think what he means is that rather than focusing on the tools, we need to be focusing on the thoughts, on the big ideas of computer science that go beyond the latest app or the latest gadget out there. And for today's session, I want to offer you 3 of these big ideas. And because I'm a children's storybook author, I would like to offer them in the form of an A, B, and C. So A stands for algorithm.
Algorithm. Algorithm. Algorithm.
The word algorithm might seem scary for many of us. We think of finance sector, we think of Facebook, but for a 6-year-old, they know an algorithm is a step-by-step instruction to solving a problem. And in Ruby's world, we actually learn the word algorithm through a story. Let's start with a 6-year-old. She's a little girl named Ruby. She's completely fearless, imaginative, and a little bit bossy. When Dad tells Ruby to dress up, she does dress up, but she leaves the pajamas on, since Dad didn't tell her to first take off the pajamas. And when Ruby is told to clean up the room from the toys, she does clean up, but leaves pens and papers on the floor. Because come on, Dad,
They are not really toys.
So, what did we learn here? Well, first of all, never argue with a cheeky 6-year-old. But more importantly, we learned that when speaking to a computer, you need to give very exact commands. You need to be very careful when you name things. The instructions need to be in the right order. And most importantly, even the biggest problems in the world are just tiny problems stuck together. And armed with this knowledge, the children will do another activity, this time teaching a computer or each other on how to brush their teeth.
So the task here is to instruct the computer to brush its teeth. The other student is the computer, the other the programmer. Let's see how things go.
So which one is the programmer, which one is the computer?
Different computer. Yeah.
How do you define the brush?
Take the yellow brush from the cup.
Good.
Take the yellow brush to your mouth. Stop. Open your mouth.
Good.
Now brush your teeth.
Yes.
So when you think about it, brushing your teeth is an algorithm, coming up with a step-by-step instruction to solving a problem. It doesn't matter if you learn to do this in Scratch, C# or JavaScript.
So this is what they learn. But they also learn about how algorithms can be very powerful. Take this cupcake. When you have a good cupcake recipe, you can make one single cupcake with the recipe, but you can also make 100,000 different cupcakes. You can make lilac cupcakes, you can make cupcakes in the flavor of banana, you can make blueberry cupcakes, you can make all kinds of cupcakes in the world. And this is the power of a step-by-step sequence of problem solving. Algorithms can be repeated over and over again, and the computer never gets bored. And the third thing I want the children to understand about algorithms is this.
Let's put these columns in order the way a computer would do it. I would start from the beginning and compare the two columns to one another. This one is bigger than the other, so let's swap them around. I would then move to the next pair and compare the two of them. Again, let's swap. This looks okay. Let's swap. Let's swap. Let's swap these. Let's swap these. And then I would go all the way to the beginning and do this over and over again until the columns are in order.
So now the children have learned the definition of an algorithm. They've learned what makes algorithms powerful. And finally, they've learned a little bit about what kind of tasks algorithms are good at and what kind of tasks humans are good at. But that is not enough. The final thing we want to show to the children is an algorithm in context. So I sometimes ask children, where in the Google search is an algorithm hiding? Or where in Facebook or TikTok is an algorithm hiding? And then finally, I ask them to build a paper cardboard YouTube. And I ask them, where is the algorithm hiding here?
Algorithms are everywhere around us, sorting, searching, recommending, and rating. Sometimes it's hard to notice an algorithm at work. In video sharing platforms, algorithms choose the ads and recommend videos because the most popular video sharing platforms, they see over 400 hours of new content uploaded every 1 minute. This means there is no way a human can go through everything. And that's where the algorithms come to play. The algorithm takes into account at least your past viewing history, the likes, watch-through rates, comments and tags to make recommendations to you. But the algorithms are also influencing the kind of videos and content we make. And that's the scary side of algorithms. Helping children explore and connect the concept of an algorithm through play and real-world examples helps them build a memory of it.
If A was for algorithm, B stands for Boolean logic. And it's a story of the biggest collection of ideas out there, which is the computer. So I absolutely love computer scientists. They are my biggest heroes. The people on the wall, they've built the modern computers from these gigantic boxes into these tiny devices that fit into our back pockets. But they did also something else while at it. They made computers very, very abstract. Nowadays, we can jam 300 million transistors at the pinpoint of a pen, but there's no way of explaining how a computer works anymore. Those of you who grew up with transistor radios, you could take apart a radio and learn how it works. That's not true with modern computers anymore. And sometimes I wish I could shrink myself to the size of a silicone chip and go inside of a computer to see how it really works. Unfortunately, that's not possible with today's physics, so I did the next best thing, which is to write a book about it.
One day, Ruby is very bored and goes to Dad's computer. But the computer doesn't work, and all of a sudden the white mouse awakes and asks Ruby for help in finding the missing cursor. Together, they fall deep inside the computer. They meet the bits, billions of tiny electronic switches that only know how to go on and off, on and off. When you combine these bits in different ways, you get the logic gates that are used to represent more complex information, like adding two numbers together. Next, Ruby and Mouse meet the hardware, the CPU that is smart, extremely busy, can calculate things very well but remembers nothing, and needs the help of the RAM, ROM, and the hard drive to keep everything in store. And of course, Ruby and the mouse meet the operating system and the software, because a computer needs very specific instructions to get anything done. And I don't want to spoil anything, but finally, after troubleshooting the software, Ruby and the mouse do find the missing cursor.
So through this very literal journey through the computer, the children learn how electricity turns into logic, how logic turns into hardware, how hardware turns into software, and how software turns into the operating systems, games, and apps we use every single day. But they also learn that while computers might be magical, they are not made of magic. They are made of logic, and that's a huge thing to learn when you're growing up. Because this generation of children, it will be the last to remember computers as a glowing box. They will not be defined in the future by a keyboard or a mouse or a screen, the computers, I mean. They will be hidden in our everyday lives, in our toothbrushes, in our teddy bears, in our teapots. And I think it's important to give kids new kinds of metaphors and new kinds of narratives to understand the technological world that is around them. One of the things that all computers share is the information processing system called input-output, or I/O. Let's look at it in more detail. First of all, in order to interact with the computer, we need input. Input is when we do something to a computer or give it information. The input could be from a keyboard, a touchscreen, a sensor, or even another program. Second, we need output, a way to get data out of the program. This could be to a screen, a pair of speakers, or another program. When computers can both receive input and send output, like for example touchscreens, we call it input-output, or I/O. Which one of these do you think is a computer? None? Well, you know, a car is a computer. It has a navigation system inside of it. And a dog might not be a computer, but it has a collar, and the collar might have a computer inside of it. And grocery stores, they have so many different kinds of computers inside of them, like the cashier system and the burglar alarm. And kids, you know what? In Japan, toilets are computers, and there's even hackers who hack them. And we go further, and I give the children these little stickers with an on-off button on them. And I tell the kids, today you have this magic ability to make anything in this room into a computer. And then once I had this little girl who came to me and took a bicycle lamp, and she said, if this bicycle lamp was a computer, we could go on a biking trip with my father, we would sleep in a tent, and this biking lamp, it could also be a movie projector. And that's the moment I'm looking for.
The moment when the kid realizes that the world is definitely not ready yet. That a really awesome way of making the world more ready is by building technology, and that each one of us can be a part of that change.
So it's through these ideas of input-output process, these ideas of computers as something else than the glowing box, that children start to have a sense of a notional machine. And what a notional machine is this mental model, this robust mental model of what a computer is good at and what a human is good at. And that brings us to the third and final letter of today, which is C, and it stands for creativity and computers. So this letter, it starts from reading the morning newspaper. Every morning, I read these news articles written by fearful reporters who state that the artificial intelligence is taking over. The AI is destroying all these jobs. The machine learning era is coming. Beware. They think of the Terminator and they think of the Skynet. And it's about artificial intelligence and our fear about the unknown. And at some point I realized that I want the next generation to have a much more optimistic and much more pragmatic idea about what artificial intelligence stands for, because they are the ones who are going to be imagining and building the future of technology. So this is the way I would explain what artificial intelligence is for a 6-year-old.
So how do computers actually learn? The human brain learns to recognize a pineapple, a hairbrush, or a cat with very few examples. Your computer, on the other hand, needs thousands of examples.
Why are we so excited about AI right now? It's because of something called machine learning. Machine learning is used, for example, in computer games, search engines, video recommendations, or phone assistants, pretty much everywhere. Machine learning became popular because all of a sudden we had data. The likes, clicks, and pictures. Lots and lots of data. The machine can be taught to identify a cat by first giving it many examples of cats. So first humans think of a problem they want to solve with machine learning and collect training data for the machine. Then the training data is fed to the computer. The human gives the machine a suitable training algorithm to solve the problem. There are thousands of different training algorithms to choose from. With the help of the training data, teaching algorithms, and machine learning, the machine builds a model. One can verify with new data that the model works correctly. The machine updates its model as it receives more information. The goal of machine learning is to find a model that answers the questions correctly most of the time. When the machine answers the question, it does not know the answer for sure, but it predicts a probability.
Artificial intelligence learns from humans what is right and wrong. But we humans can also move our own prejudices to the computers and accidentally teach the machine wrong. Many of the strange decisions made by the computers happen because the training data is biased. Can you figure out what the computer misunderstood? What is the bias? And what kind of examples would you include in the training data?
Finally, why all of this matters? Well, I think having a language makes us understand and have agency over our surroundings. A few years ago, I read this article on The Guardian, and there was this story about British school children who were shown 2 sets of pictures. And one set of the pictures had Pokemon species on it, and the other set of pictures had different kinds of plants and animals and natural world objects in it. And the British children, they were much better, by far, in recognizing the Pokemon. So they had much more vocabulary to describe the Pikachu than the birch tree, or the Bulbasaur than the badger. And the researchers were really worried because what happens in a world where you don't have vocabulary to describe what is happening around you? And I'm worried about the same thing. I want there to be 7 different kinds of words for snow in Finland. But I'm also worried about the word of technology, where we are having this same kind of disappearance of vocabulary. Because in technology, we have these things I like to call the suitcase word, where we pack a lot of things inside of the suitcase, things and definitions, and then we throw that suitcase to another person, and we never unbox them, we never open them up. These words, they include words like algorithm, blockchain, Bitcoin, artificial intelligence. But they also include more innocent words like internet. Once there was a little boy who came to me and said, "Linda, is the internet really a place?" And I told him, "Oh no, it's not a place. It's this interconnected network of computers around the globe. And you can think of it like the information superhighway, or the global village." And then I realized I sound like a kid of the 1990s. This child, he has never pressed the disconnect button of the modem. The internet is something that is invisible everywhere around him, and I need to come up with better metaphors of explaining what the internet is.
Is the internet the fiber optic cables that go from the bottom of the sea all the way to the space? Or rather the protocols that define how the data travels around the world 8 times in a second? Or is the internet what happens when you connect the 6 billion of us, the cat videos, the memes, the Gangnam styles? This is the challenge with teaching technology. It's the hardware, software, and societal change, all at once. Most of our childhood learning is not stored in books, screens, and assessments, but in memories, textures, and sounds. Early childhood computing education benefits from a dose of mud pies, mushrooms, and make-believe, a sense of wonder, and a sense of adventure. Giving children a language to talk about computers gives them a way to describe the world and its complex technological systems, to pay attention, and to cherish and reclaim. The first step, I think, is to make us understand, then love the world, and then take better care of it.
At its best, technology gives us confidence. At its best, vocabulary gives us a sense of ownership and belonging. It doesn't become this random spell, this magical utterance from the world of Harry Potter, but something that we own and we can trust. And to really build the computing curriculum of the 21st century, to really equip our children, we need to start unbundling these words and making them understandable and tangible. And it starts with the very word of technology. So I'm going to end with 3 short stories and definitions about the word technology. Because you see, nowadays we think of technology as tablets or fancy railway systems or these modern ideas. But really, technology comes from the Greek. And the Greek stated that technology is skills and competencies and tools to solve a problem. And for the Greek, agriculture, it was technology. And the democracy, that was technology too. And it's really interesting that they chose to include these very human abilities, like skills and competencies, into the definition of technology. Another definition of technology comes from José Ortega y Gasset, a Spanish philosopher, and he talks that technology is superfluities. Today, as in the Paleolithic era, Ortega y Gasset believes that animals are atechnical because they are content with the simple act of living. And I'm not a philosopher, but if I understand Ortega y Gasset correctly, I think what he's saying is that technology and the ability to build tools has to do with our human imagination and our human storytelling capability. So armed with these 2 definitions, the idea that technology is profoundly human and that it has its roots in our imagination and in our storytelling capabilities, I'm going to leave you with the final definition of technology. And this time it comes from a 6-year-old little girl. And she says, technology is electricity that loves. It is used to play. I use it to have a conversation with my mother. We use a WhatsApp application. And then finally, and most importantly, people uses technology. Thank you very much.